I want to find f prime of x, the derivative of f of x, for, let's say, f of x equal to, sure, let's have some fun. Let's say x cubed plus 2x. And the words I'm not going to write down here is using the limit definition, right? So once we get past this limit definition stuff, we probably won't use it very much. So generally, if someone asks you to find this derivative, you would just use the power rule. And we're still in limit definition mode. So we're going to say, okay, well, the derivative is the limit as h goes to 0, or delta x goes to 0, of f of x plus h minus f of x all over h. If someone says use the limit definition to find the derivative of a function, this is always where you should start. Or with delta x, right? The limit is delta x goes to 0 of f of x plus delta x minus f of x all over delta x. And then you have to throw your function into the whole mix. So it's going to be the limit as h goes to 0. So f of x plus h, well, f of x is x cubed plus 2x. So f of x plus h is x plus h cubed plus 2 times x plus h, and then minus f of x, so minus x cubed plus 2x all over h. That's our beginning. And then we have to do a couple things. So remember our ultimate goal, make that h cancel out. Our before that goal, make all the not h things in the numerator cancel out. So we have to factor out x plus, or multiply out x plus h cubed. When we multiply out x plus h cubed, you can multiply out like the long way, like x plus h times x plus h times x plus h, but there's kind of, there's actually a nice pattern for multiplying out x plus h to a pattern. Let me show you guys that pattern real quick, because it is kind of cool. So there is this thing called Pascal's triangle, and it starts like this. The 1, and then a couple more 1s, and then each subsequent row has 1s on the outside, and the middle parts are the two kind of diagonal things above it added together. So the next row is going to be 1, 2, 1, because 1 plus 1 adds to 2. The next row is 1, 3, 3, 1, because the 1 and the 2 add to 3, and the 2 and the 1 add to 3. And then it keeps going, 1, 4, 6, 4, 1, and so on, and so on, and so on, forever. Pascal's triangle is really neat. There are really lots of really cool patterns in it. Like, let me say really one more time. There are lots of really neat patterns in it. But one of the cool patterns is that these numbers in each row are the coefficients of the binomial expansion. Meaning, if you write out, say, x plus h to the 0th power, well, anything to the 0th power is just 1. I know these are kind of lame ones to start with, but it helps see the pattern. X plus h to the 1st is 1x plus 1h, which we would normally just write x plus h. X plus h squared, as I'm sure you've seen a few times at this point, is 1x squared plus 2xh plus 1h squared. Again, you don't need to write those ones, but I'm emphasizing the fact that you get 1, 2, 1. And then x plus h cubed, so it's going to be 1 times x cubed. So the coefficients are going to be 1, 3, 3, 1. And the way the powers work is, if it's to the 3rd power, you start with your first thing to that power, and then the powers of that get 1 less each term, and the powers of the other part get 1 more each term. So the next term is 3x squared times h, and then the next term is 3 times x times h squared, and then the last term is 1 times h cubed. And this goes on and on and on, right? You could do, I know I'm kind of, my rows are not, my rows here were too close together. Right? This one's going to be x plus h to the 4th would be 1 times x to the 4th plus 4 times x cubed times h plus 6 times x squared times h squared plus 4 times x times h cubed plus 1 times h to the 4th. So if you ever have to multiply out x plus h to some power, you can just write down the rows of Pascal's triangle until you get to the appropriate row. How do you know which row it is? Well, if it's the 4th power, you need the row whose 2nd term is 4. If it's to the 5th power, you need the row second, right? Whatever power it is, you look for the row with that second number being that power. And then you have all the coefficients. So back to the problem we're doing, that means that we can say that x plus h cubed is x cubed plus 3x squared h plus 3xh squared plus h cubed. And then distribute the 2, 2x plus 2h. And then distribute the minus sign, minus x cubed minus 2x. All divided by h. And then things cancel. Specifically, the things that don't have h's. X cubed and negative x cubed. 2x and negative 2x. So we end up with, oh, no, right, everything else has an h. H there, h there, h there, h there. So you can either divide each thing by h or you can factor out an h first. I like to factor out the h. This is the limit as h goes to 0 of divide out an h or factor out an h. We've got a 3x squared plus a 3xh plus an h squared plus a 2 all over h. This h divided by that h cancels out. Leaves you with a 1 times all this. And then you can either write one more line or you can just say, okay, the rest of the h's go to 0. So you get 3x squared plus 3x times 0 plus 0 squared plus 2. So we end up with 3x squared plus 2. And that is your derivative of x cubed plus 2x. Questions about this? We're going to do a few more examples. What I will say, so if you have questions, let me know. But what I will say is, for ones like this that are polynomials, meaning just nice positive powers of x, the process is very, very much straightforward in that you always just multiply out the whole thing, and the things that don't have h's should cancel, and then everything else you divide on h. So for ones that are polynomials, where you just have like x to a power plus a coefficient times x to another power minus another thing, right? It's very, very straightforward. For other types of functions, it's a little more complicated, like there's usually an additional step or two, but it's always the same idea generally. Yeah, of course, Marshall. And if you Google Pascal's triangle, like you will find millions of pictures of it, right? It's a very, very well-known thing. But yeah, Pascal's triangle, pretty cool. There are lots of really cool things that I should not start talking about because they're not important for what we're doing. But I will just say Pascal's triangle has lots of neat things in it. Yeah. Let me go ahead and erase this side. I'll leave that up for a second. Pascal's triangle does come into play when we start talking about how the power rule is actually proved, but we won't get there quite yet. So let's go ahead and do a couple more examples that are not quite so easy. Let's look at one like this. Let's do it. So we'll do a couple hard examples and a couple easy examples, then we'll talk about the power rule. So let's look at something like this. Let's say our function is x over x plus 3. Notably, not a polynomial, right? That's a rational function. You don't have just positive powers of x in the numerator. You have a denominator of that. Okay. So if I'm trying to find the derivative using the limit definition, we're starting out the way we always start out. With the limit, as h goes, I'll try and switch back and forth between delta x just so you guys can see it. But again, it's really the same thing using delta x or h. You should be comfortable either way. But here we'll use delta x just for fun. So its limit is delta x goes to 0 of f of x plus delta x minus f of x all over delta x. You don't have to write this out every time, but I really, really encourage you to make sure you know what you're supposed to be doing, right? This is always the starting place for a limit definition of the derivative question. So if someone says, use the limit definition of the derivative, or just says use the definition of the derivative to find the derivative of the function, this is where we're starting. And you should, for sure, on your, if you guys already talked about this in Abby's class, she will definitely ask you about this on your first test. So I have to imagine, Marshall, that is only true in the beginning. Like I believe she has said that, but I feel like she might not have clearly communicated her intention there, because definitely as time goes on in 16a, we move away from always writing out the definition. So I would ask her for clarification about that, because eventually we're going to learn the power rule, the quotient rule, the product rule, the chain rule. And it's just, I've never seen that be the case before, that someone always wants you to write the limit definition. So I would say, I can't imagine she really meant that specifically. And I would encourage you to ask for clarification, because it becomes unreasonable to actually do that every time. But for now, that's probably what she means. Is, at least at this moment in our class, we should always be writing out the limit definition, because that's all we've got. So here, it's going to get a little bit messy. The limit is delta x goes to 0. So f of x plus delta x is going to be this, but everywhere there's an x, I'm going to write x plus delta x instead. So I'm going to have x plus delta x over x plus delta x plus 3 minus f of x, which is just x over x plus 3, all over delta x. Yeesh. Okay, so here is the deal. Whenever you have fractions, and so this is why we spent kind of time dealing with 0 over 0 limits earlier in class, because all of these limit definition of the derivatives are 0 over 0 limits. And just like before, when we had 0 over 0, if there were fractions, we got a common denominator. That's what we're going to do here. It can be a little misleading, right? You might think I can just throw in a delta x here to get the common denominator. We cannot. Our common denominator is not particularly nice. It's the product of these two denominators, x plus delta x plus 3 times x plus 3. So our common denominator here is x plus delta x plus 3 times x plus 3. And so here's the nicer way to do this. The nicer way is to multiply the top of this fraction and the bottom of this fraction by that common denominator. So we're going to write this as the limit as delta x goes to 0 of, okay, so you get a bit messy, x plus delta x over x plus delta x plus 3 minus x over x plus 3 times this common denominator on top and bottom. So x plus delta x plus 3 times x plus 3 over the same thing. Okay. The effect of doing this is that we're going to get rid of these denominators in the numerator here. Right, when I multiply this, so when I distribute this, or I'm distributing this to each of these terms, right? And then my arrows are a little misleading here, right? It's not each individual part, it's the whole thing. Sorry, I know that kind of looked, right? It's all of this distributed here and there. So when I multiply all of this by that, the denominator cancels. The x plus delta x plus 3 cancels. So those cancel, and you're left with x plus delta x times x plus 3. So this times the first term gives me the numerator x plus delta x times the x plus 3. Minus, when I multiply this times this, the x plus 3's cancel, and I'm left with x times x plus delta x plus 3. And we know, since we're trying to make this delta x cancel out, there's no good reason to distribute it to all that. We're just going to leave the denominator as delta x times x plus delta x plus 3 times x plus 3. Questions about this step? It's funny, one of the classes, like I'm watching one of the classes I'm co-classing for, and she always asks her questions. She's like, okay, I know you guys have to have questions because you guys said things about this earlier. If you don't have questions, that's fine. I just think it's kind of funny. Some people are like, I'm really going to wait until someone asks a question. I'm not going to wait because it's the only one that has questions. But if you have questions, speak up.
I have a question.
Okay, go ahead.
Okay, so for was the numerator part, you know how you said it cancels out? So the x plus 3 cancels out the one on the bottom, right? And
Right.
then that one's the one. Okay.
Right.
And then it's like distributed. Okay.
Right. So this whole thing is multiplying by each of those pieces there.
Okay. From
So,
top and bottom too, right? Like,
right. But the thing is, on the bottom, well, on the bottom, I'm not. There's no distributing to do because I'm
oh no,
not.
I meant like just the numerator because you know how both of them, like there's the fractions that I was talking about, like top and bottom.
Right.
Okay.
Yeah. Yeah. I think we're on the same page. Okay. So now, remembering our ultimate goal is to cancel out this delta x. We need all the things in the numerator that don't have a delta x to go away. So we're going to multiply it all out, and then hopefully all the not delta x things cancel out. And do I have enough room? Never. I never have enough room. I think I can make this fit. Let's see. So my denominator is still delta x times x plus delta x plus 3 times x plus 3. The numerator, so when I FOIL this out, let's see what I get. I get x squared. I get x times 3. I get delta x times x. This is the one I don't like when you have a delta x times x, because I feel like people accidentally write like delta x squared, which is not true. And then finally 3 times delta x. And this is not going to fit because I'm not good at writing small. So I'm going to write it terribly up here. So distributing the minus x, we're going to get a minus x squared, a minus x times delta x, and a minus 3x. Sorry for the gross writing it all over the placeness. Canceling stuff, I see that the x squared and the minus x squared cancel. The 3x and the minus 3x cancel. And the delta x times x and the minus x times delta x cancel. So we're left with a 3 delta x on top, which is great because 3 delta x divided by delta x, the delta x's will cancel. So the next step, we can say, all right, I have the limit as delta x goes to 0 of 3 over x plus delta x plus 3 times x plus 3, because we canceled this delta x with that delta x. Or we divided that, if you want to say it that way. Since we've now canceled out the delta x that we wanted to get rid of, we can let the rest of the delta x's go to 0. So we end up with 3 over x plus 0 plus 3 times x plus 3. Or more normally written as 3 over x plus 3 squared. This seems like a reasonable limit definition question to have on a test, but definitely on the harder side of limit definition derivatives to ask. Let's do one more kind of hard one, and then we'll do a couple easy ones that show us a couple specific things. And then I think we're ready to talk about the power rule. Unless there's other things you guys want to see. Sorry, dropping caps. I did this and then went back. Okay. Let's do this one. Let's use a different function. Let's say our function is the square root of, I don't know, 4 minus x squared. That seems minorly awful. So g prime of x is going to be, again, the limit definition. The limit as h goes to 0, g of x plus h minus g of x all over h. You probably don't have to write this every time, but it's good that you know it. Right? You definitely should have this definition memorized on lockdown, right? Like for sure. And do make sure you've got it right. It's always x plus whatever you have here, either h or delta x, and then it's minus g of x, right? Because again, it's the difference in the y's, right? The y values of the g is the function values, right? Function value minus function value over the difference in the x's, right? That there is your x plus h minus your x, which is just h. So make sure you've got, I've seen too many people put a plus sign there. It's a minus sign, be careful. And too many people put a minus sign there. It's a plus sign there. All right, step. Limit as h goes to 0 of, I'm going to have the square root of 4 minus x plus h squared minus the square root of 4 minus x squared. And in the past, we've seen that when we're subtracting something from a square root, we have to multiply by the conjugate. So we're going to rewrite this as the limit as h goes to 0 of the square root of 4 minus x plus h squared minus the square root of 4 minus x squared over h times the square root of 4 minus x plus h squared plus the square root of 4 minus x squared over the same thing, right? Because we're only ever allowed to really multiply by 1. Okay, so when you multiply out the conjugate, so when I multiply this whole thing by this whole thing, the middle terms cancel and you get the square of the first thing minus the square of the second thing. So we end up with the limit as h goes to 0 of this thing squared is just the insides. It's 4 minus x plus h squared. And minus this thing squared is just 4 minus x squared. Over the denominator, which is going to be h times all of that. So h times the square root 4 minus x plus h squared plus the square root of 4 minus x squared. Okay. So now, just like every other time, we want the not h things in the numerator to cancel. So I'm going to do a couple things at once here. Limit is h goes to 0. Do make sure when you're doing a limit definition problem that you write the limit in each step until you actually let h go to 0. It's definitely worth a point. So I know that x plus h squared is, right, we know this part right here, that's your x squared plus 2xh plus h squared. But it's 4 minus all that. So we have to distribute the minus sign and get 4 minus x squared minus 2xh minus h squared. And then distribute this minus sign as well, minus 4 plus x squared. All divided by the same denominator, h times the square root of 4 minus x plus h squared plus the square root of 4 minus x squared. And then we see in the numerator, the not h things do cancel out. 4 and negative 4, negative x squared, and positive x squared. I should also point out, sometimes some of the h things do cancel out. Our goal is that every not h thing cancels, and then it's okay if other stuff cancels too. Like in the previous one, right? In the previous problem, all of the not delta x things canceled, right? The x squared and the 3x. We also had the thing with delta x cancel. That was fine. So we're left with the limit as h goes to 0 of, so I have a negative 2x h minus h squared. Let's factor out an h. So I have an h times a negative 2x minus h over h times all of that stuff. The square root of 4 minus x plus h squared plus the square root of 4 minus x squared. And then this h cancels with that h. The rest of the h's go to 0. So we get negative 2x on top. We get the square root. By the way, this is why I didn't multiply that x plus h squared down there, because I knew that h was going to go to 0. So typically, especially in the denominator, we don't usually multiply things with h because we're pretty sure usually the rest of the h's go to 0. So it's going to be the square root of 4 minus x squared plus the square root of 4 minus x squared. The square root plus another square root is 2 of those. So you can simplify this as negative 2x over 2 times the square root of 4 minus x squared. You can even cancel a 2 and just say it's negative x over the square root of 4 minus x squared. Questions, concerns, comments? All right, I'll go erase the other side. This is one advantage to not teaching in the classroom is I can erase the other side of the board which is not a thing when the board is on the wall. Silver linings, silver linings.
Wait, I have a question. I'm so sorry.
No, not at all. Don't be sorry. I asked you for questions. What's your question?
Oh, so you know how it's like negative 2x and then the denominator is a 4 minus x squared square root and then it equals that. I wanted to ask, like, how did you cancel the other like 4 minus x squared?
So I didn't. What happened was I had negative 2x, and when you add something to itself, like when I add 5 plus 5, I get 10, which is when I add something plus something, I get 2 times the something. But then the 2 divided by the 2.
Oh, okay. Okay. Thank you.
You're very welcome. Yeah. All right. A couple easy but still important examples. So what if my function is, say, I don't know, 6x plus 3? And I want to find the derivative, also known as the slope of the tangent line, right? That's at least one interpretation, is the slope of the tangent line, or the rate of change as of the function as x changes. Well, for this equation, we know it's a straight line. Right? This line looks something like this. And if I want to find the slope of the tangent line, well, no matter what point I pick, the tangent line is the line itself. So this is something that's true for straight lines. There really isn't a nice idea of a tangent line. For straight lines, the tangent line is itself, right? The line that goes through this, its tangent is just itself, which just feels dumb to even try and draw. The point I'm trying to make is that for a straight line, the slope of the tangent line is just the slope of the line itself. So we already know, before we even get going on this problem, well, what's the slope of this line? I know I often ask questions and then answer them, but I'm actually asking you guys. Yeah, it's definitely 6. So we already know, before we take the derivative here, the answer is going to be 6, because that's the slope of the line. We should still do it, but I just want to let you guys know, for these straight lines, for any line, we know what the answer is going to be. Unless it's a vertical line where the slope is undefined, then the derivative doesn't exist. Okay, so, but that's not a function, so we don't have it really. So limit h goes to 0, f of x plus h minus f of x all over h. So here we're going to get the limit as h goes to 0. F of x plus h is going to be 6 times x plus h plus 3 minus 6x plus 3. Do make sure that when you're subtracting f of x, you put parentheses around all of it so that you make sure you distribute your minus sign. Distribute the 6, distribute the minus sign. I suppose an equal sign would also be good here. So the limit as h goes to 0 of 6x plus 6h plus 3 minus 6x minus 3. And just like every other time, the not h things cancel out. So here I get the limit as h goes to 0 of 6h over h. But 6h over h is just 6. So we have the limit as h goes to 0 of 6. Okay, so what's the limit as h goes to 0 of 6? Well, 6 is just 6. And it doesn't matter what h is doing. If h goes to 0 or h goes to a billion, this has nothing to do with h. It's like, forget about h. There's no h's here. I don't care what h is doing. So if you've got more specifically, if you have the limit of a constant, you always just get the constant. So there's our answer, derivative of 6. And it works whether your line has a positive or a negative slope, or even a slope of 0. That's the other example I want to do. If our function was, say, g of x equal to something like, I don't know, 8, which is a horizontal line which has a slope of 0, we know the derivative is going to be 0. We can still show it using the limit definition, but I want to stress both of these because their derivatives come up often. You should be really, really comfortable saying, hey, look, a constant function, oh yeah, a constant function has a slope of 0. Its derivative is 0. A straight line function, oh, we know the slope of a straight line. It's just the slope. And the derivative is just the slope. So here, it's the limit as h goes to 0 of g of x plus h minus g of x all over h. Well, here's the thing. G of x is 8. G of anything is 8, right? G of 1 is 8. G of 2 is 8. G of a million is 8. G of x plus h is 8. G of x is also 8. And here's where people get a little caught up. So I've got the limit as h goes to 0 of 0 over h. And you're thinking, well, I can't cancel anything. How do I make that h cancel out? Well, we don't really. What we say instead is, well, here's the deal. And this is where it's important to actually remember what a limit means. This is the limit as h approaches 0, which means h is getting very, 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 very close, but not equal to 0. So h is a very, very, very small positive or negative number, but it's a very specifically not 0. All right, so let me ask you guys, what's 0 divided by 3? Right, exactly. What's 0 divided by, I don't know, 0.000001? You guys already answered. Right, exactly. Doesn't matter what you're dividing by, as long as it's not 0. 0 divided by any non-zero number is 0. H is a non-zero number, right? Because h is approaching, but not equal to 0. So what we do here is we say, oh, well, this thing, before I even think about the limit, this thing here is 0. So this is the limit as h goes to 0 of 0. And then the limit of a constant is just the constant. The limit of a constant is just the constant. So that's how the limit definition works for this. It seems like it's actually kind of, even though it's a very straightforward derivative, it can be actually a tiny bit confusing. But that's the process for this. So limit definition, here's what I'll say about it. We definitely, and so actually to go back to Marshall's comment about the professor saying to always use limit definition, she is right. What I'm going to say about that though is we're going to develop rules that we use. We're going to develop the power rule, the product rule, the quotient rule, the chain rule. But there are going to be some functions that don't kind of like fall into any of those categories. So when we encounter a new function, like a trig function, like sine of x or cosine of x, often what we do is we say, well, I don't know how to take the derivative of this new function. I'm going to go back to the limit definition and see what it tells me. So that is one, I will say she is right to say that. We're always going to kind of at least start with functions of, if we don't know how to take the derivative of this thing using a rule that we have got, we're going to use the limit definition of the derivative. When the problem doesn't say to use the definition, we don't have to use it. Good. Yeah, that's appropriate. With the problem, yeah. So you should only, yes, exactly. If you words. So if the problem, I should really just leave it there. Marshall has explicitly written it correctly. If the problem doesn't say to use a limit definition, you should not use a limit definition. You should only be using the limit definition if the problem on your test says to, the homework says to, you're in the chapter of the book that is the limit definition chapter of the book. But really, most of the time, we're not going to be using the limit definition of the derivative unless you're asked to. Or it's a new type of function, we need to go back to the drawing board. So let's talk about the power rule. Yeah, I think we're in a good place to talk about the power rule. Sure. Sorry, I just want to see one thing. Oh, yeah, okay. Oh, actually, let me do, what time is it? Oh, yeah, it's time. Let me do one more limit definition question just because there's kind of an added thing. So let's use the limit definition of the derivative. To find the equation of the line tangent to, let's say, f of x equal to, let's be fun, 4 over x at the point, Sure, 4 comma 1. Let's do that. So we're trying to find the equation of a line, meaning we need a point, got it, and a slope. We don't have it, but we know how to find it. This is what the picture is going to look like, kind of. Not that you don't have to draw a picture at all here. I just want to kind of show you guys, right? The function 4 over x looks kind of like this. Where is that function discontinuous? It's discontinuous at 0, which means it's also not differentiable at 0, because you have to be continuous to be able to be differentiable. There's more than just that, but that's one of the conditions for differentiability. You have to be continuous. So here's the point, 4 comma 1, and we're trying to find the equation of this line that is tangent to it. So at least just looking at the graph, I am pretty convinced that my derivative at that point should be negative, because it looks like the slope of the tangent line is for sure a negative slope. So let's find it. So we're going to find the derivative using the limit definition. Limit as h goes to 0. So I'm going to write f of x plus h. I'm actually just going to write it out. So f of x is 4 over x. F of x plus h is 4 over x plus h minus f of x, which is 4 over x all over h. And just like the other problem we did that had fractions and fractions, we multiplied the top and bottom by the common denominator. So what's the common denominator of 4 over x plus h minus 4 over x? It's not just x plus h. Yeah, it's typically, or I mean, it'll always work to just use the product of the two denominators. There might sometimes be a lesser common denominator, but typically, especially with these limit definition problems, the best bet is almost always just say, okay, I'm going to take the two denominators and multiply them together. There's your common denominator. Great. Totally works every time. Works all the time, 60% of the time. Works all the time, not 60% of the time. Works all the time. So this is going to be the limit as h goes to 0. We're going to distribute this to the top. So when you multiply this by this, the x plus h is canceled, and you get 4x. When you multiply all of this by this, the x is canceled, and you get 4 times x plus h. And the denominator, we don't multiply out. We just get h times x plus h times x. Simplifying the limit as h goes to 0 of 4x minus 4x minus 4h over h times x plus h times x. Why am I not multiplying out the denominator? For a bunch of reasons, right? I want that h to cancel. And then I also know that this h is going to go away at the end, so I don't need to take the time to multiply it out because I'm just creating extra work for myself. 4x and minus 4x cancel. So I'm left with the limit as h goes to 0 of negative 4h over h times x plus h times x. The h divides the other h. So then I've got negative 4 over x plus h times x. And then the remaining h's go to 0. So I get negative 4 over x times x, which is x squared. So there's my derivative. It's negative 4 over x squared. So then that's the slope of the, so I should say that's the derivative at any value of x. It's the slope of the tangent line at any value of x where it exists. Clearly doesn't exist at 0, right? If you plug in 0, it would be undefined. But if I want to find the slope of the tangent line at this point, I'm going to plug in x equal to 4. So f prime of 4 is going to be negative 4 over 4 squared, which reduces to negative 1/4. And then to find the equation of the tangent line, well, now I've got my slope, I've got my point. Use whatever formula you prefer to find the equation of the line. My preferred method is to use the point slope formula. So to say y minus the y coordinate equals the slope times x minus the x coordinate. So in this case, that would be y minus 1 equal to negative 1/4 times x minus 4. And some people are totally cool with you leaving it this way. Some people like you to solve for y. So if you can leave it this way, leave it that way, because you're not going to give yourself the opportunity to make any arithmetic errors, right? So if someone says to not simplify, take them up on that deal. Don't simplify. Don't simplify unless you have to. But if we do have to simplify, then we should. So simplifying this, we get, let's see, y minus 1 equals, I'm going to distribute the negative 1/4, negative 1/4 x, negative 1/4 times negative 4 is positive 1. And then we add 1 to both sides to get y equal to negative 1/4 x, and 1 plus 1 is 2. So that would be the y equals mx plus b, or the slope-intercept form. Alternatively, you can do the thing where you start with y equals mx plus b, you plug in negative 1/4 for m, and 4 for y, and 1 for x, and then solve for b. That is also perfectly fine. That's just not the way I usually do it. Problem is, when I open a new pen, I just want to use it all the time because it works great, and then it just dies super fast. So I should try to need to space out my pen usage, just because I have very few blue pens left. How many refills? The blue is more expensive, so we didn't buy it. All right, now let's talk about the power rule. Let's use a different color pen, James. Sure, green. Green's good. Also, notation. I should probably maybe speak about notation for just 1 second. So, notation. Often we say to find the derivative, right? If you're finding f of x, if f of x is your function, the derivative is f prime of x. But there's lots of other ways you can write it. Sometimes people will write, if I want to take the derivative, to take d dx of f of x, which I often use this kind of notation actually a lot. If people are saying the function is y, they might also write y prime. They might also write dy dx. These are probably the most common notations. Someone might do something silly and write something like f sub x. This is more of a notation that comes up in 16C. I wouldn't expect to see it in this class, but it could. I think one of the teachers mentioned it very briefly. But there's lots of different notations for derivatives. I think I can erase this. Actually, yeah, sure. Yeah. Sorry. Like, there we go. Now let me erase it. At least let me leave. I'll do that. I think it's time to wash the board down. So let's talk about the power rule. The power rule for derivatives. So the reason I wrote this is because I like to write it a different way. So one way you could write it is for f of x equal to x to the nth power, the derivative is n times x to the n minus 1. So when you're taking the derivative of x to a power, it's just that power times x to the 1 less power. Another equivalent way of writing this would be to say the derivative with respect to x of x to the n is equal to n times x to the n minus 1. The nice thing about this notation is that you don't have to say the function is this and then the derivative is this. You can just say the derivative of the function is equal to what it's supposed to be equal to. So that's the power rule, and it works great. It works for any power of x, as long as you have written it so that you've just got x to a power and nothing else interfering with that. So if I was going to say, like, my function was, I don't know, x to the 7th power, the derivative would be 7 times x to the 6th. This is going to be your favorite derivative to take, right? The power rule is like, it's like, oh yeah, power rule, great. But it does take a little bit of practice because sometimes things can be a little bit strange. And let me actually grab this other page here for one. Whoa, don't do that. Yeah. So what if instead my function was something like, I don't know, f of x equal to, yeah, let's do that, sure. X to the 10th plus the 5th root of x minus 7x plus 9. So typically, before we use the power rule, we want to write everything as x to a power, if we can. So the only problem here really is that I don't have x to a power here. All right, the fifth root of x, I need to rewrite that. Notice I'm not writing the derivative because I'm not taking the derivative. I'm writing the function because I'm just rewriting the function. The fifth root of x is x to the 1/5 power. You can write this as x to the first if you want. And you could write this as 9 times x to the 0 if you wanted. I don't think either of these are necessary, but I want to find out that you can do it. So now let's take the derivative. The derivative of x to the 10th is 10 times x to the 9th. The derivative of x to the 1/5. So again, I just think of it as the power coming down in front. So I've got a 1/5 times x to the 1/5 minus 1 is 1/5 minus 5/5, which is negative 4/5. The derivative of 7x to the first, so you could either say, well, I know the derivative of 7x is 7, because 7x is like a straight line, and the derivative of a straight line is just the slope. Or you could actually use the power rule and say, okay, well, the 1 comes down, and 7 times 1 is 7, and then you get x to the 0. X to the 0 is just 1. And then finally, the derivative of 9, the derivative of a constant, the slope of a constant is just 0. Or you could say, it's kind of weird, but you could say, okay, the 0 comes down, and 0 times 9 is 0. Doesn't matter what x is because 0 times anything is 0. I don't think you need to do any of this. I think it's perfectly fine to look at this and say, like, oh yeah, obviously the derivative of negative 7x is negative 7, and the derivative of 9 is just 0. So our answer here would be 10x to the 9th plus 1/5 x to the negative 4/5 minus 7. There was something else here that I wanted to say. Oh, yeah. Notice, or don't, that we have implicitly used one of the rules for differentiation. We've used the rule that if you take the derivative of a bunch of things added together, you just take the derivative of each piece and add it together. That's one of those rules that's kind of a rule that we use all the time, but we never like explicitly say we use it. But yeah, there's a rule that says if you take the derivative of f of x plus g of x, it's equal to the derivative of f of x plus the derivative of g of x. That's what we did here, but we're never going to say that we did it. Also, it's true whether you're adding or subtracting. It's not true if you're multiplying, right? The derivative of f times g is not the derivative of f times the derivative of g. For that, we'll need the product rule later. Yeah, let's do a few more of these. Oh, by the way, here's another example, actually. So we found that the derivative of 4 over x was negative 4 over x squared. And that is true whether you do it the long way or you use the power rule. So I'm going to write it this way. The derivative of 4 over x, well, to use the power rule, we have to rewrite it as x to a power, meaning it can't be in the denominator. So I have to rewrite this as the derivative of 4 times x to the negative first. And then the derivative of 4 times x to the negative first. So the constant multiple hangs out. So yes, the derivative of 4 is 0, but the derivative of 4 times a function is just 4 times the derivative of that function. That's another one of those rules that we kind of use all the time, but we don't really explicitly state. Normally, I wouldn't write this. Normally, I'd just jump straight for the following. Sorry, I know there's a lot of stuff written on the board still. Normally, I would jump straight to saying, okay, I get 4, and the derivative of x to the negative first is negative 1 times x to the negative 1 minus 1 is negative 2. But really, I would have multiplied the negative 1 by the 4 and gotten negative 4 times x to the negative second, which is exactly what we got for the derivative, just written in a slightly different way. Either way of writing it's fine. You can write it as negative 4x to the negative second. You can write it as negative 4 over x squared. And there's good reasons to pick one way or the other. If I had to take the next derivative, if I had to take the second derivative of 4 over x, I probably want to write it like this so that taking the next derivative is easy. If I want to think about the domain of the derivative, I'd probably write it like this, because here it's more clear that 0 is not in the domain, where here it's a little less obvious that you can't plug in 0. I will state 0 to a negative power is undefined, because really that's just division by 0. So let's do a couple more of these, and then I might talk about how the power rule actually works, yeah, or where it comes from. Let's do another one. Let's find, say, the derivative of, let's make it exciting. Sure. 7x to the 5th plus the cube root of x to the 11th minus 5 over x cubed plus 2 over the square root of x. And for this problem, for any problem like this, we definitely want to rewrite it so that we've got just powers of x. So I'm going to rewrite this. So I'm still haven't taken the derivative yet. So I'm going to write this. And this just means, right, I mean, it means the derivative of whatever's over here with respect to x. But you should just say, oh, that's just an instruction. It's an instruction telling me to take the derivative. And so until we've taken the derivative, we have to keep writing down that that instruction is still there. So 7x to the 5th is still 7x to the 5th. I don't want to say like 35x to the 4th and then simplify these. You either are simplifying or differentiating. You're not doing sum of each. This is going to be x to the 11 thirds. Right? It's x to the 11th to the 1/3 power. Minus, this is going to be 5 times x to the, I've seen people struggle with this before. When the power changes places in the numerator or denominator, it just changes signs. So if it's x to the 3rd in the denominator, it's x to the negative 3rd in the numerator. Same deal here. This is 2 over x to the positive 1/2, which is going to become 2 times x to the negative 1/2. And now we're ready to differentiate. So power rule. The power just comes down. So when it comes down, it's multiplying. So you could think of this as 7 times 5x to the 4th, but let's just do 7 times 5 and get 35x to the 4th. Plus the derivative of x to the 11 thirds is going to be, well, the 11 thirds comes down. 11 thirds times x to the, let's say we're not so good at subtracting fractions. If we can't do that in our head, that's perfectly fine. Let's just write 11 thirds minus 1. Because we know that's what's supposed to happen, right? We're supposed to subtract 1 from the power. And then the negative 3 comes down and multiplies the negative 5 to get positive 15. X to the negative 3 minus 1 is negative, not 6. Is it this one or is it this one? Is it negative 2 or is it negative 4? Yeah. But be careful. It's easy to like think, oh, 3 minus 1 is 2. But it's not. It's negative 3 minus 1 is negative 4. When you subtract from negatives, they get more negative. And then finally here, okay, so the negative 1/2 comes down. 2 times negative 1/2 is negative 1 times x to the negative 1/2 minus 1. Let's just write that one out. And then we should simplify. So 11, or fix these. 11 thirds minus 3 thirds is 8 thirds. And negative 1/2 minus 2 halves, so negative 1/2 minus 2 halves, negative 1 minus 2 is negative 3, so negative 3 halves. So just be a little extra careful with those fractional powers when you're subtracting 1. It's not too terrible, but it is a little terrible sometimes. Yeah. Times, okay. So why does the power rule work? Well, it's kind of because of Pascal's triangle. So here's kind of the deal. Oh, sorry, it's pen all over my hand. So we said that the derivative of x to the n is equal to n times x to the n minus 1. Well, we can actually show this is true for a positive integer power if n is a positive integer number. It's actually true for any n, But let's assume for a second n is a positive integer. So let's look at what x to the n looks like. Well, oh, sorry, not x to the n. Apologies. Let me back it up for a second. I'm going to find the derivative. I'm going to do it the long way. I'm going to use the limit definition. So the derivative of x to the n is the limit as h goes to 0 of f of x plus h, which is going to be x plus h to the n minus f of x all over h. So right, just so everyone's on board. This part is not super duper important, but I think it's kind of important, right? I mean, it's definitely important to know where things come from. I definitely encourage you to believe the things your teachers say, but it's also nice to be like, oh yeah, there's actually a reason why this works, not just because my teacher said so, even though right, teacher saying so is not a good reason, but they shouldn't be lying to you. I guess I should also point out, right, my function is x to the n. So to find the derivative of x to the n, the limit definition says we would do this. Well, what do you get when you multiply x plus h to the nth power? Let's take a look. Should have, see, this is where if I had like lots of board space, I would have written Pascal's triangle somewhere on the other side of the room and then be like, look, there it is. But we'll write it again. So here's Pascal's triangle, 1, 1, 1, 2, 1, etc. And so I'm going to say this is the 0th row, and it gives me x plus h to the 0. Or at least the coefficients. So this is the first row, and it gives me x plus h to the first equal to x plus h. This is the second row, and it gives me x plus h squared. Or the coefficients, all right, 1, 2, 1. So notably, the name of the row is the name of this is the value of the second entry. So, and this is not the 0th row, right? But like the second row, the second entry is 2. The third row, the second entry is 2. The fourth row, the second entry is 2. So if I want to find x plus h to the n, I need to use the nth row, right? X plus h squared is the second row. X plus h cubed is the third row. So I need the nth row, but the nth row, the second entry is n. I'm not going to write out what all of them are because they're kind of complicated, but I know that for the nth row, it's 1, and then n, and then some other number, and then some other number. And then the last couple entries, well, there is symmetry. The last couple entries are also n and 1. Not that they matter. These two entries are really the only things that matter. So when I write out x plus h to the n, here's what I get. X plus h to the n is 1 times x to the n plus n times x to the 1 less power times h to the first, and then plus some other number. Let's give this, let's call it like this. This is C2, this is C3, right? They're constants. And then x to the 1 less power, h to the 1 more power, all the way to the last couple terms. The second to last term will be n times x times h to the n minus 1. And the very last term will be 1 times h to the n. So that is x plus h to the nth power. I mean, obviously not being super specific about what these values are. Okay, so let's go back to the other side of the board and see what we get. So here's what we get. Because the limit as h goes to 0 of x plus h to the n, which we just said was 1 times x to the n plus n times x to the n minus 1 times h plus some other constant times x to the n minus 2 times h squared plus all the way to the last couple terms, which were n times x times h to the n minus 1 plus h to the n, and then minus x to the n. Ooh, sorry, my n's sometimes start to look like h's. I see someone's written something. Sorry, one sec. Yeah, of course. Go ahead. Yeah, if you get the dentist appointment. So I just want to reiterate, not to like point out Carl or anything, but in general, right? This class, while I'm happy to have you here, I think it's valuable. It is kind of the least important thing in your life. So if you've got other classes to go to, office hours, your teacher is holding, a dentist appointment, please feel free to go and don't even feel like you need to ask. Right? If you've been here for an hour, you're definitely going to get marked as being here. I always go look at the attendance from Zoom and check to see who's been here. Even if you're only here for like 5 minutes, I'm still going to mark you here, right? As long as you show up, you're going to get credit for being here. So don't feel like you have to ask. Thank you for asking. I don't mind you asking. It's certainly fine. But just know you're welcome to come, welcome to go. I'm not the most important thing in your life. There are much more important things. You should take care of them. The dentist, super important. Take care of your teeth. Good teeth, important. So yeah, go to the dentist. Hope it goes well. Hope you don't have any cavities. Back to this. Notice, just like every other time, the non-H things cancel out. Everything else has an H. H to the first, H to the second, the next one will have H to the third, H to the fourth, all the way to H to the n minus 1, H to the n. So then I'm going to factor out an H from the rest of the terms. So with a limit, as H goes to 0, I factor out an H from everything, and n times x to the n minus 1. And then here I've got a C2 times x to the n minus 2 times h to the first. Then everything else is still going to have an h in it because everything else had a power of h that was 2 or higher. So I've got lots of other things. This second last one is n times x times h to the n minus 2. And this last one after I factor out an h is going to be h to the n minus 1. All divided by h. This h cancels that h. The rest of the h's go to 0. There's a lot of them. 0, 0, 0. Everything in here, 0. What are we left with? N times x to the n minus 1. The power rule. So that's why the power rule, or at least that's how we show the power rule works for like positive integer powers of x. And then we just kind of generalize and say it works for any power. So there is some justification for you. In case you were curious, this is how we kind of prove to ourselves, oh yeah, the power rule actually does work. Not just because someone said so, because it actually works. Yeah, we got 17 minutes to save the world. Okay. Or to do some math, one of the two things. Yeah, let's do another example here. Oh, that's a good question, sure. Let's look at f of x equal to, x squared minus 3x plus the fourth root of x minus 5 all over, that's gross. Let's make it a little bit different. Yeah, really? I don't love that. That's sure fine. 2x to the fourth. So I want to find the derivative of this. After this example, can you flip back? Oh, I can go back to this. I can go back right now. Wow, my wife is getting very loud with someone on the phone. Probably one of her employees. She's the manager. Anyway, that's not important. Let's get back to this. So when you have something like this, you certainly could, if you knew it, use the quotient rule. But even if you could, you shouldn't. Because although the quotient rule is fine here, it's much, much easier to simplify this. And this is generally the case. When you have some sort of quotient and the denominator has one term, it's usually the right thing to do to divide each thing by that term. So I'm going to rewrite this as f of x equal to x squared divided by 2x to the fourth minus 3x divided by 2x to the fourth plus the x to the 1/4. I'm going to change it to a power instead of a root divided by 2x to the fourth minus 5 divided by 2x to the fourth. And then I'm going to rewrite all of those as x to a power. So for the first three, when you have x to a power divided by x to a power, you subtract the powers. So 2 minus 4 is going to be negative 2. This is going to be x to the negative 2. And what's the coefficient? It's not 2, it's 1/2. Because that 2 is in the denominator. Here, the coefficient is going to be minus 3/2. And then x to the first divided by x to the fourth is going to be x to the negative third. Here it's going to be even grosser. I'm going to get a 1/2. X to the 1/4 divided by x to the fourth, you're going to subtract those powers. 1/4 minus 4 is 1/4 minus 16/4, which is negative 15/4. And then here we're going to get minus 5/2. Since there isn't an x on top, we just say, oh, the x to the fourth comes up to the numerator, and we change the sign to be x to the negative fourth. And now that we've written everything as x to a power, where x is in the numerator, not the denominator, we just use the power rule. And depending on your comfort level, you can multiply straight away or do it in kind of two steps. So you could bring down the negative 2 and say 1/2 times negative 2 is negative 1. Or you can take the extra step and just say, okay, I've got 1/2 times negative 2 times x to the negative third. I've got minus 3/2 times negative 3 times x to the negative fourth. This one's going to be even especially gnarly. What is the x1 of x before the 5/2 one? This one here? Oh, this one here. Yeah, negative 15/4. Yeah. Yeah, because 1/4 minus 4 gave us 1/4 minus 16/4, which is negative 15/4. So then the derivative of that's going to be, let's see, 1/2 times negative 15/4 times x to the negative 15/4 minus 1. Negative 15/4 minus 1. It's okay to write this. You still need to simplify it at some point, but it's perfectly fine to take an intermediate step. And then the last one's going to be minus 5/2 times negative 4 times x to the negative fifth. So simplifying, 1/2 times negative 2 is negative 1. I'm just going to write negative x to the negative third. Negative 3/2 times negative 3 is going to be positive 9/2, because that's negative 3 over 1. And fractions times fractions, you multiply the tops and the bottoms together. So negative 3 times negative 3 is 9. 2 times 1 is 2. So 9/2 is x to the negative fourth. 1/2 times negative 15/4 is going to be negative 15 over 8. Times x to the negative 15/4 minus 4/4 is negative 19/4. And this last one, negative 5/2 times negative 4 is going to be positive 20 over 2, which reduces to 10. X to the negative fifth. And that would be our derivative. If you want, and some people want this, some people like to rewrite it where the powers of x are positive. So if you really wanted to, you could write this as negative 1 over x cubed plus 9 over 2x to the fourth minus 15 over 8x to the positive 19/4 plus 10 over x to the positive fifth. I don't think that's necessary, but sometimes people ask you to do that. So just be aware. Sometimes people are like, please write your answers as positive powers. I don't think that'll usually be the case, but it could happen. Yeah, here's a good question that I think is reasonable. Definitely use the skills that we already have. I feel like this next question is on the verge of a possible like extra credity kind of question. Like it's hard enough that it could be extra credit, but not super hard. So the question is, at what points, like there might be more than one, does the tangent line to x squared plus x pass through the point 4, 16? So that's what we're looking for. We're asking where on this function does the tangent line go through that point, which should not be on the function. Graphically, here's kind of what this looks like. This is a parabola. It looks vaguely like this. And the point 416 is somewhere like maybe over here. And what we're asking is somewhere, probably, on this graph, there's a point where the tangent line is going to go through, right, through. It's going to go through that point there. And so the question is, what's the point on the graph where the tangent line through that point goes to this other point? Okay. So here's what they're really asking you to do. They're asking you to find the slope of this line in two different ways and then say they have to be equal. So there's a point there. I don't know what it is. Neither do you, right? We're trying to figure out what it is. Let's call it something. You can either call it x comma y, but really we should call it x comma x squared plus x, because the y coordinate has to be x squared plus x. So yeah, I think I want to do that. So this point here is x comma x squared plus x. And our job is to figure out what that point actually is, like to find the value for x. So here's what we're going to do. We're going to find the slope of this tangent line in two different ways. One way, what's one way we can find the slope of a tangent line? Using calculus. The derivative. So one way we can say, well, the slope at that point, well, I know how to find the derivative. The derivative is the derivative of this function, which is 2x plus 1. I'm using my power rule. Derivative of x squared is 2x. The derivative of x to the first is just 1, right? Derivative of x, the slope of x is just 1. Okay. But then we can find the slope of this line another way. We can say, oh, I have 2 points. I know how to find the slope of a line between 2 points. I'm using the slope formula. So the slope is y2 minus y1 over x2 minus x1. And you can kind of go either order. It usually makes sense to do the variable things minus the known things. So I'm going to say this is my x2, y2, and this is my x1, y1. Either way is fine. It's just usually easier if you do these ones minus these ones. So my slope is going to be x squared plus x minus 16 over x minus 4. All right, now here's the thing. The slope of this line is the same as the slope of this line, meaning the slope calculated this way has to equal the slope calculated this way. So we set these two slopes equal to each other and try and solve for x. So let's see, I've got not enough room is what I've got. So I've got 2x plus 1 equal to x squared plus x minus 16 over x minus 4. And the very first thing I'm going to do is multiply both sides by the denominator x minus 4. So I'm going to rewrite this as, fine, let me show my work. It's good to show your work. So we're multiplying both sides by x minus 4. X minus 4. On the right side, we just get the numerator. So on the right side, we get x squared plus x minus 16. On the left side, we have to FOIL it out. So x times 2x is 2x squared. X times 1 is x. Negative 4 times 2x is negative 8x. And negative 4 times 1 is negative 4. And then we bring everything to one side. I'm going to pick the left side because that's the side that has the bigger power of x squared. So I'm going to bring everything to the left. 2x squared minus x squared is 1x squared. X minus 8x is minus 7x. And then minus another x is going to be minus 8x. And add 16 to both sides. Negative 4 plus 16 is 12. And then if the person who's written this problem is kind, this will factor, which it does. This factors as x minus 2 times x minus 6. So the solutions are x equal to 2 and x equal to 6. Now we're not quite done because the question asks for what points, not what x values. So technically we have to find the y coordinate as well. So the points are going to be, well, if x is 2, The y coordinate is 2 squared plus 2. So the point's going to be 2 comma 6. And if I plug in 6, 6 squared plus 6 is 42. So these are the answers. Graphically, you might be wondering, well, how are there 2 points? Well, here's what's really happening. Yeah, there's nowhere to erase. I'm gonna flip the board over and erase on the other side. So what's really kind of happening here is if your graph looks like this, and let's say your point's like here, there's one point up here where the tangent line does this, and there's one point over here, right? And that's how you're getting 2 different answers, because there's one point over here where the tangent line hits it there, and there's one point over here like that. So kind of an interesting problem. I could definitely see it being a question that someone could ask on a test, and it's not super unreasonable. What else? I feel like there was something else I wanted to say before we wrap things up here. There was something I was looking at that she had up. Sorry. Sometimes you run out of gas at the end. You're like, oh, what do I do now? Yeah, let's go. Oh, there was something for real. Fine. Let's do one more limit question, or a limit question, just because I know people still have been asking me about this. So here's a question. Find the horizontal asymptotes of this function. F of x equal to 6x plus 5 over the square root of 9x squared plus 4x plus 1. Yes, this is one of those problems where you're going to have a different answer if you go to infinity or negative infinity. So first and foremost, right, the way you find a horizontal asymptote of a function is by finding the limits to infinity or negative infinity. So let's do the limit to infinity. And I know for this kind of thing, when you've got a square root of x squared, usually you're going to factor out the x squared. So I'm going to have 6x plus 5 on top. And the bottom, for the 9x squared plus 4x plus 1, I'm going to factor out x squared. I'm going to be left with 9 plus 4 over x plus 1 over x squared. What's the square root of x squared? Well, in this case, it is x, but more generally, it's the absolute value of x. So I want to make it very, very clear. The square root of x squared is the absolute value of x. Because the square root of x squared, no matter what you put in, you always get out a positive thing, right? Because you can't take a square root and get out a negative thing. Square root of 9, 3, not negative 3. Square root of x squared, absolute value of x. So since x is positive, the absolute value of x is just x. And then we can divide everything by the highest power of x, which is just x to the first. So you can rewrite this as, this is going to look kind of weird. Limit as x goes to infinity of 6x over x plus 5 over x over x times the square root of 9 plus 4 over x plus 1 over x squared all over x. Here, these x's cancel. Here, these x's cancel. And you're left with, okay, so we let x go to infinity. 6, 5 over x gets super small. And then you make the square root of 9 plus 4 over x gets super small. 1 over x squared gets super small. So you get 6 over 3, which is 2. On the other side, okay, I'm going to do the cheater teacher thing here. I'm just gonna be like, okay, so if we go to minus infinity, okay, it's a little lame, fine. In fact, I'll just write in the minus infinity, right? How about that? So we do the limit as x goes to minus infinity. The only difference is instead of x, now the absolute value of x is minus x. Right? If x is, say, negative 72, the absolute value of negative 72 is negative 72, which would be 72. So here, you get the opposite sign.